Question is about thermodynamics. Question 7. Question about thermodynamics. Explain why standard entropy value for carbon dioxide is greater than that of carbon. Well, carbon dioxide and carbon. The reason the standard entropy value for carbon dioxide is greater is because CO2 gas is more disordered. Remember, gases are more disordered than solid, than carbon, which is a solid. Gas is more disordered than solids. Say the temperature at which the standard entropy value of aluminium is 0. Well, the temperature is just going to be 0 Kelvin. Or absolute 0. And if we're going to use 0, it's going to be in Kelvin, the units. And then 7.3, use the equation of Dayton table 7 to calculate minimum temperature in Kelvin at which the reaction becomes feasible. So first things first, we need to calculate the entropy change, which is equal to entropy products minus entropy of reactants. Products minus reactants. Entropy change equals products 4Al, so 4 times by 28 plus, because how do I know it's 28? Because this is the S entropy and that's formation data. So 4 times by 28 plus 3 CO2, 3 times by 214 plus 3 times by 214. So 4 times by 28 plus 3 times by 214, products minus 3C minus 3 times by 6 plus reactants 2 times by 51. Now don't put it all in the calculator because your calculator probably work out wrong. First do it step by step. So 4 times by 28 plus 3 times by 214. 28 times by 4, 112 plus 3 times by 214. 754 minus, well, 18 plus 2 times by 51. That looks like 31, but it should be 51. 2 times by 51. 120. Entropy change equals 754 minus 120, 634. 634, and remember the units, joules, K to the power minus 1, mole to the power minus 1. So that's that. Now we need to work out delta H. Delta H equals products minus reactants. And obviously I can write the full equation, but delta H you should know by now. Did in year 1 as well. But if you don't know, yeah, just remember products minus reactants. So it's going to be, well, we know 4Al is going to be 0. So it's going to be 3 times by minus 394. 3 times by minus 394 minus reactants minus 2Al2O3, 2 times by minus 1669. 2 times by minus 1669. Are there any other reactants? Well, you got 3 carbon, but it's an element by itself, so it's 0. So therefore you got delta H equals 3 times by minus 394 minus 1182 minus 2 times by minus 1669 minus 3338. 2 negatives become a positive, so we're left with delta H equals minus 1182 plus 3338. 2156. 2156, and that unit's in kilojoules per mole to the power minus 1. And now finally, to calculate minimum temperature which reaction becomes feasible, we need to use Gibbs free energy change. Delta G is equal to delta H minus T delta S delta G equals delta H, which worked out as 2156, and what we did, entropy of products, formation products minus reactants, minus temperature in Kelvin, oh yeah, temperature is what we're trying to find. And we should know that when we're trying to calculate the minimum temperature at which reaction becomes feasible, delta G is equal to 0. So this one's a bit more complicated, because usually it just tells me to find out Gibbs free energy change. But here what we actually have to do, I got a bit too carried away. We know delta G is equal to 0. Delta G is equal to 0. So we get, and then move this to the left hand side, we get T delta S equals delta H. Therefore T is equal to delta H over delta S. Delta H is 2156 over delta S, which is 634. However, delta H is in kilojoules per mole to the power minus 1. Delta S is in joules to joules k to the power minus 1 mole to the power minus 1. And we're trying to find it in Kelvin. So what we have to do is divide the delta S by 1000 to convert into kilojoules per mole to the power minus 1. And we get 2156 over 634 times by 10 to the power minus 3, 3400. 3400 Kelvin, and that is the minimum temperature at which a reaction becomes feasible. So when a reaction becomes feasible at minimum temperature, Gibbs free energy change, Gibbs free energy change is equal to 0. And then make it equal to 0, rearrange the equation, delta G is equal to delta H minus T delta S, therefore 0 is equal to delta H minus T delta S, therefore T delta S is equal to delta H, therefore T is equal to delta H divided by delta S. We got delta H by doing entropy of products minus reactants. We're using the formation data in the table 7, and we found delta S entropy change by doing entropy of products minus reactants using the data in table 7. We get this, however, delta H is in kilojoules per mole to the power minus 1, delta S is in joules, k to the power minus 1, mole to the power minus 1, so we need to divide this by 1000 to get it into kilojoules per mole to the power minus 1, and therefore you get your final answers as 3400 Kelvin. And that's the end of question 7.